Nowadays, when you take a flight, for example, you can pay a little bit more for your ticket, and it's kind of offsets the carbon of your flight. A lot of airlines offer this. Someone has to go capture that carbon dioxide on your behalf.
Sure. Mm-hmm.
And you can imagine if you're a really, really big company, I won't name any so we don't get in trouble, but if you're a big company, like a software company, you don't really produce a technology that you can try to decarbonize. A lot of your energy consumption is in running servers, for example. There's nothing you can do about that. So if you want to become a carbon neutral company, your best approach is to pay another company. You pay another company to capture carbon on your behalf.
Hello, and welcome to Research Matters, Cornell University's video podcast putting a spotlight on research that aims to solve real-world problems. I'm your host, Laura Riley. Today we're talking about climate change and a fresh twist on one of the most urgent challenges we face: how to pull carbon dioxide out of the air or from power plant emissions in a way that doesn't itself add more pollution. With us is Professor Phillip Milner, Associate Professor of Chemical and Chemical Biology at Cornell. His lab at Cornell University recently developed a novel system that uses sunlight, not fossil fuel energy, to capture and release carbon dioxide. It's a breakthrough that could reshape carbon capture technology worldwide. Hi, Phillip. It's great to have you here.
Yeah, thank you for having me here.
So I guess, first of all, for all of the non-sciencey people among us, including myself, why is carbon capture such a vitally important thing?
Rising atmospheric levels of greenhouse gases are causing significant changes to our climate. We're starting to see that a little bit now, and it's only going to get worse. And so we need to think about how we're going to reduce those levels in a way that doesn't that we reduce those levels to minimize climate impact, but without causing further damage. And I think that's the problem. A lot of the technologies we've developed require fossil fuel combustion kind of counterintuitively to power them in order to operate. So we really need to think about how we can reduce the levels of greenhouse gases in the atmosphere in a sustainable way that will help us kind of minimize climate change for future generations.
Why can't we just lean heavier on emission reduction and cleaner cars and et cetera?
Yeah, that's a great question. So I can kind of break down a little bit about the different ways we can tackle this. I think we're going to need hundreds of solutions to tackle this. It's a huge problem. I mean, the scale is something we cannot fathom as people. It's something like 40 gigatons of CO2 is how much we release as a species into the atmosphere every year. And that's just thousands of times more than anything else that we produce. And so we need many, many different solutions. So energy transition is a big part of it. But that's not going to help with everything. For example, solar doesn't work very well in Ithaca. We need many different energy transition options for different places around the world. But also there are a lot of sectors in industry that are very hard to decarbonize. So big ones that people don't really know much about are steel and cement production. They're about a quarter of all global CO2 emissions come from those. And it's very hard to envision, what are we going to use instead of concrete? What are we going to use instead of steel? And so inevitably to decarbonize those sectors, we're going to have to do carbon capture. So that's part of it. And the energy transition part of it is that we can't transition fast enough. We're still going to need to burn fossil fuels for the next 50 years, transitioning hopefully from coal towards natural gas, which does release less carbon dioxide. But we're still going to be burning natural gas 50 years from now to power different sectors. And along the way, new technologies are also going to arise that are very energy intensive. We're seeing that right now with AI and data centers. And so that shock kind of demand of more energy means we're going to probably be burning fossil fuels for that. So I think the goal should be in terms of energy transition, we get away from fossil fuels eventually, but we're not going to be able to do it in the time scale that's fast enough where for the next 50 or even 100 years, those emissions are still going to be going into the atmosphere. So we have to do something about post-combustion. It's called capture from power plants. But also these industrial sectors like cement and steel that are hard to decarbonize, those we also need carbon capture for as well.
So I want to just back up a little bit. So we have carbon capture, which is kind of the grab, and then carbon sequestration, which is kind of the putting it away.
Yes.
So in terms of the grab, what are the main mechanisms that we use now, and are they all fossil fuel intensive?
Yeah, so the main way that we do carbon capture right now, I guess I'll say the main application we use it for is actually as part of natural gas production. We have to remove carbon dioxide from natural gas when we harvest it from the ground. And so that's where a lot of the technology development has come from. And that we use these molecules that are called amines. It's not that important what they are, but they selectively react with carbon dioxide out of a mixture of different gases, and they can pull it out of the mixture. And why that's important is that step we have got to work very well. We have many different ways of doing that. The next step is the hard one, though, because now you have this molecule that has pulled the CO2 out, and you need to take the CO2 back off so you can reuse it many, many, many times. And then you could take that CO2 and either turn it into something, use it to carbonate sodas, or sequester it underground. So that step, which is called regeneration, that is where all the energy goes. You have to put in energy to break that strong bond and release the CO2 molecule back. And right now, the way that we typically do that is we burn fossil fuels to produce the energy. We either heat up the molecule so it releases that bound CO2, or we pull vacuum on it. We reduce the pressure. Those things are all very energy intensive. So that's the way we do it right now. And I think that you can see that, for example, many estimates say that if we were to go do post-combustion carbon capture at every power plant in the United States right now, we could do it, but the cost of electricity would go up by about a third or maybe about 40% because of the parasitic load.
All right, listeners say no way on that right
exactly.
now. Absolutely.
Yeah, that's no way we can do that. So we need to think of a way to not use the energy of the power plant to power the capture unit to remove CO2 from that power plant. That's just not going to really work very well.
All right, so let's talk a little bit about the research that you're doing. So I think in May, you had some research that came out that to me sounded very magical, kind of utilizing sunlight in this process. What did you do?
Yeah, so there are a lot of people who've been interested in alternative ways of removing CO2, this regeneration step, using different types of energy inputs. And so we in my lab have been interested in photochemistry or using light to drive chemical reactions for a while now. And so actually the graduate student who's the first author on that paper, Bayu, he's the one who came up with this idea that what if we could use light as the energy input, both for the CO2 capture step and for the CO2 releasing step of a carbon capture process. Using it for both steps had never been done before. There was some work previously about using light for either the capture or release, but putting it all together means that we can kind of distribute the energy demand and really just use light as the only real energy input for the system. So that's how that works. And essentially what we do is we take a molecule that's very inexpensive. It's something like $1 a kilogram. We shine light on it and it kind of triggers it to become like a trap for carbon dioxide, and it reacts very selectively with it. And then we switch the pressure. We kind of pull vacuum on it for now, and we shine light on it, and it releases the carbon dioxide back that we can kind of capture and release over and over again.
Releases it where? Releases it into
what you usually would do is you would take a stream of dilute carbon dioxide, so the emissions of a power plant or even potentially air. And then what you produce is pure carbon dioxide that you could then use for conversion into something, sequestration, or like I said, you can carbonate sodas and beer with it as well. So what you're doing is you're turning dilute carbon dioxide into pure carbon dioxide. And so that's what we usually release it into, is just pure carbon dioxide gas that we can do something with.
So I think I read that there was some inspiration from plants. Mm-hmm. Can you explain that connection?
Yeah, let's see if I can explain the chemistry behind that. But so most carbon capture technologies are based on nitrogen or oxygen-based molecules. But actually the way nature fixes carbon dioxide is using a carbon-based molecule that reacts with the carbon dioxide. And so that's where that happens in the enzyme rubisco in plants. We fix carbon dioxide by using a carbon-based molecule. And so our system very closely mimics that chemistry, using a carbon-based molecule to capture the carbon dioxide. That's very, very rare in terms of the chemistry of how this works. And also the release step is also precedented there are enzymes that achieve this, what's called decarboxylation process, where they remove the carbon dioxide from a molecule. And so we took some inspiration from how enzymes do that as well.
So, all right, this experiment, have you tried it outside the lab? Like how would that scale and what would that look like?
We have tried it in the window of our lab using the sunlight from
I don't know if that technically is outside the lab.
It's not outside
right?
the lab, but it's the closest we've gotten so far. We did it in the window. A little bit of a tricky experiment to do in Ithaca. You have to find the right day where the sun is shining strong enough that we could do it. We just use a magnifying glass.
It's not a ringing endorsement of Ithaca.
Yes, this technology is something we would probably want to do somewhere like Texas, for example, in West Texas.
How about Hawaii?
Or Hawaii would work great too. But yeah, I guess we have done it that way. We did have done it in the courtyard of our chemistry building as well. So we have used real sunlight to actually power it, as well as simulated sunlight. So that's the closest we've gotten so far to getting it out of the lab. The other thing that we have done that is more advanced, I think it's something we definitely can talk about, is we also showed that our system could work on real flue gas that we got from Cornell's heat and power plant.
Great. So what did that look like? How did you orchestrate that, and what did you find?
Yeah, it's a great story, and I think it led us to a really exciting project we're doing with the Cornell Atkinson Center right now. So what we actually did is we just went to the power plant and asked them, can we have a bag or have some of your actual flue gas? So Cornell has a natural gas-fired power plant on campus. It produces a flue gas stream. It's about 10% carbon dioxide, and mostly the rest of it's nitrogen, oxygen, water. We asked them, can we get some? And they actually loaded up.
This is just a byproduct of.
Yeah, it's a byproduct of electricity
What do they do
production.
with it ordinarily?
They just vent it into the air.
Okay.
So they just release it into air. It's called flue gas. It comes out of basically the flue, the smokestack of the power plant. So they just release it into air, but they do test it all the time. So they're good about making sure no weird impurities got into it. So they collect it a lot. And so we asked them,
what is it? It's like
a garbage
balloon
bag.
Okay.
Yeah, it's basically a garbage bag filled with gas. And we asked them, when you're testing it, can you give us some? And they gave us a few essentially garbage bags with a little nozzle on it filled with gas. And we showed that we could capture the carbon dioxide from that.
It's like the weirdest gift ever.
I know.
It's a bag of flue gas.
But it led to some interesting conversations with people at Cornell, in particular with Tobias Honrath, who's in chemical engineering, about how difficult it is for academic and even industrial scientists to get your hands on this flue gas. Because you can imagine if you go to a commercial power plant, you say, give me some of your flue gas, they'll be very hesitant because they don't want anybody to know what's in that stream, right? But Cornell has no skin in this game, right? They don't care if we publish what is in our flue gas, right? And so it got us talking about, can we make it really easy to get access to samples of flue gas? This is really difficult for academic researchers.
So now it's about capture of flue gas, right?
Exactly. So can we get real samples? And everybody uses simulated gas, but can we get the real stuff? And so we approached Cornell Atkinson Center with an idea to build what we call Capture Lab. The acronym very cleverly spells out the word capture, about how we can provide samples of gas for people to test their catalysts or scrubbers that can remove carbon dioxide. And so we're in the process of trying to get this online. Atkinson Center funded it. We're going to basically put a trailer that can go to the Cornell power plant, and people can run experiments on actual flue gas instead of simulated kind of mixtures. So we're hoping that will be online next year. And that was all inspired by us just getting garbage bags of this real gas to test our
Sounds very
technology
unsexy,
on.
but very cool, right?
Yeah, and I think we're hoping that it will help streamline the advancement of the translation of technologies from the laboratory, where we tend to use, we can go buy a cylinder of 10% CO2 and nitrogen. But the real flue gas has trace impurities, it has trace oxygen and things like that in it that can really mess with scrubbers. And so you really want the real stuff.
Was it problematic in this case? I mean, were the kind of
No,
impurities?
our molecule was totally okay with it, but it's very well known that these trace contaminants, in particular oxygen, can be a real problem for current technologies and lead to degradation. That's a big challenge also when you're trying to pull carbon dioxide out of air, because air has a significant fraction of oxygen. That's what we need to live, right? But that oxygen oxidizes things, like iron turning to rust, right? Or steel turning to rust. That's what can happen to a lot of scrubber technologies. Ours so far seems to be okay with it. And so that's a real advantage as well over current technologies. So that's something that people tend to miss because you use these simulated mixtures. But if you've got the real stuff, you can't hide from those impurities, right? So that's what we're hoping we can push, especially the academic community, to test out their technologies on a real carbon capture challenge.
So what would it look like if industry adopted this? How would it scale? What would it look like? And what benefits would accrue to the industry or their bragging rights?
So scaling it up, I think we're working on that now. And one of the big kind of, inspirations, of course, is solar technologies or photovoltaic solar cells. You could imagine having essentially a solar cell that pulls in the light, but also pulls carbon dioxide in from the air, for example, it just pulls air in and then removes the carbon dioxide from that air as it's running. So that's kind of what we envision, what we're
So
trying to push towards.
a dual system, essentially, a solar.
Yeah, it would look something like a solar panel. Whether you could also harvest electricity at the same time as you're doing all of this to power a little bit of the, we do have to, for example, change pressure. So we do need a little bit of electrical input for that. That's something we've talked about, kind of a dual system. Doing that requires us to make some advances on the chemistry where we can move from, right now our molecule is dissolved in solution, but we need to translate it to a solid material that we can you could imagine coating on top of a solar cell, for example. So that's what we're trying to do now. I think the advantages are that, you kind of have, we haven't talked very much about direct air capture. We've been talking about industrial, what's called post-combustion capture, either from cement and steel production or from fossil fuel combustion. You can remove that carbon dioxide, but also you can imagine pulling carbon dioxide out of air, which has some advantages in terms of not requiring you to work with oil and gas companies or cement and steel manufacturers. Anybody could go put a direct air capture unit in their backyard, for example. So it's a little bit more democratic, a little bit easier legislatively to make happen. The downside is that it's more energy intensive to do because carbon dioxide is pretty dilute in the air. It's causing lots of problems, but it's actually a very minor fraction of air. So there's in flue gas, it's pretty concentrated. In air, it's pretty dilute. Direct air capture is one way you could imagine going here. That's very easy to envision what it could look like. And that's something where you're pulling carbon dioxide out of air, which is benefiting everyone. And then the key to that is that the carbon dioxide you get has to be useful for something.
So you wouldn't just sequester it then.
Well, you would
capture it and use it, as you said, in something like.
But you could still sequester it, and its value then would be in the form of, for example, carbon credits. Like nowadays, when you take a flight, for example, you can pay a little bit more for your ticket, and it's kind of offsets the carbon of your flight. A lot of airlines offer this. Someone has to go capture that carbon dioxide on your behalf.
Sure.
So a lot of the direct air capture startups and companies that are advancing right now, that's one of the ways that they can go is these kind of carbon credits. And you can imagine if you're a really, really big company, I won't name any so we don't get in trouble, but if you're a big company, like a software company, you don't really produce a technology that you can try to decarbonize. A lot of your energy consumption is in running servers, for example. There's nothing you can do about that. So if you want to become a carbon neutral company, your best approach is to pay another company. You pay another company to capture carbon on your behalf. So that's where the value can also be in sequestration. And so
agriculture is obviously a big area where they thought credits were going to be, kind of an ancillary revenue stream for all of these struggling farmers. With like a third-party audit like Indigo or one of those big companies, that was going to be a moneymaker. And I think it's been a little wobbly, but
it is tough because I think the tricky thing is, if you go to a company and you say, we'll sequester, $300, $400, $500 a ton for you, that's a lot of money to be investing. And so kind of our mission is how do you make that number be smaller? And the Department of Energy has put a number of $100 a ton as something you want to shoot for example. And so I think that to do that, you need lower energy, lower cost technologies to do this. That's kind of where the basic science side is trying to push towards, I would say. Yeah.
All right. So your lab does more than just carbon capture. So I know that you've done kind of research on sustainable catalysts, light-driven chemical reactions to reduce environmental toxins. What are the other things that you've been working on or the other questions that you've been asking?
Yeah, good question. Our lab works on a lot of different areas related to sustainability and in terms of both chemical production and also these separations, which are, something like 15% of global energy use. And so the way we think about this is we combine aspects of chemistry and also material science and chemical engineering together to try to design solutions that we can use to make fine chemicals, that means drug molecules, agrochemicals, much more sustainably from inexpensive building blocks. They often tend to be gas molecules like carbon dioxide. But for example, some of the gases we work with, these hydrofluorocarbons, they are tens of thousands of times more potent greenhouse gases than carbon dioxide. And so we have a lot of interest in how do we take those gases and turn them into drugs.
What are the industries that release those?
There are a lot of different industries. So there's probably a dozen of these fluorinated gases. Together, they are about 2% of anthropogenic greenhouse gas emissions. So a lot of it is from refrigerators, the refrigeration industry, but also semiconductor manufacturing, polymer manufacturing. So Teflon production, for example, for nonstick pans produces this greenhouse gas called fluoroform
Yep.
that our lab has done a lot of work with to try to turn into drug molecules. We see this kind of beautiful synergy that we have these gases that are kind of hurting the environment, but they are inexpensive, great building blocks for chemists to use. And over here, we have a chemical production industry that's based mostly on petroleum and not that sustainable. And so if you can take these cheap gas molecules, capture them, and then turn them into drugs and agrochemicals, you can kind of create this sustainable ecosystem.
Sure. Take
Of course,
fossil fuels out of the loop. Sure.
yeah, people are, of course, thinking about this with carbon dioxide, how to turn it into various things. But I think there are other greenhouse gases as well. Nitrous oxide, you mentioned agriculture, that comes mostly from agriculture, from fertilizer. Methane is a big problem too. It comes from many different sources, and then these fluorinated gases. So we are interested in how do we capture all of those, and then how do we turn them sustainably into different chemicals.
Do you work on methane? I know Cornell has a lot of research just because there's the
methane
ag school.
Methane is the real big challenge. I mean, carbon dioxide is a challenge because of the scale, but in terms of the chemistry, it's reactive enough that you can design chemical reactions that can work to capture carbon dioxide. But there's other greenhouse gases that's much more difficult. They're much more inert chemically. So methane is one of the most inert gases. So finding a way that you can pull methane out of air, I would say, is a grand challenge for the community that we're part of. No one has a great technology to do that. Our lab has not done too much with methane because it is really, really difficult. And we focused on particularly these fluorinated gases and carbon dioxide, and also a little bit nitrous oxide. Methane is a really, really big challenge. And I think it's in the United States, methane is probably as much of, if not more of a problem than carbon dioxide. As we switch more and more to natural gas, when you burn it, produces less carbon dioxide than coal, which is good. But methane, the main component of natural gas is methane.
Sure.
So everywhere it leaks out of a pipeline, it actually is worse than if you just burn some coal.
Okay.
Because it's 40 times more potent a greenhouse gas in the short term than CO2. So it's tough. That's a tough problem. Methane is a really, really hard one. That's probably our real next big grand challenge, to figure out what to do about methane emissions.
All right. So I want to, before we end, talk a little bit about, listeners hear segments like this and they say, okay, we're screwed. There's nothing we can do. Are there behaviors or lifestyle changes or directions that the average person can go or adopt that may move the needle nominally?
Yeah, it's a good question, because it can feel a little overwhelming if you look at the numbers that most of anthropogenic greenhouse gas emissions come from industry, from electricity production. And so, the standard thing you always hear, it's a little bit trite, but it is true. If you lower your thermostat a few degrees in winter, raise it in summer a few degrees, make sure you turn lights off and things like that. Electricity production is the biggest contributor to all of this. And so saving electricity and, not taking unnecessary trips, things like that, those things can all help. But because this is such
we should stop using AI, right?
AI is an interesting one, because if we can harvest the power of AI to design better climate solutions, it could be great. But in the short term, it's definitely going to present a big challenge because of energy. It needs a significant amount of energy to operate.
Right, that's so why AI, no crypto.
They certainly presented a fun challenge to think about for electricity. We I think until recently were imagining electricity scaling one way, and now it's got to scale electricity demand in a much different way. And that's where I say, going back to what we said originally, we are going to need to burn fossil fuels for a while. We're still going to be burning them in 2100. It would be my guess if I had to bet money on it. And there's people that are smarter than me that say the same thing, which is why post-combustion carbon capture sometimes, for example, has been called a distraction from energy transition.
Yeah.
But
or
we
somehow,
need every solution.
Enabling.
Yeah,
not
we're enabling us to
forward.
stick with fossil fuels for longer, which is probably true. It could lengthen the time that we still burn natural gas if we can capture the carbon from it.
But it also seems honest.
It's the honest assessment. That's why I say, solving the climate crisis is going to take 1,000 solutions, and one of them will be that we'll still be burning fossil fuels. So if we just ignore those emissions, it's going to present a problem. So I guess those are the things, it comes from the greenhouse gas emissions come from many different sources, but even small things like not upgrading your refrigerators and air conditioners and things. A lot of the really old ones leak these fluorinated greenhouse gases. They're really bad. You have to treat them properly to dispose of them.
So the low
things
E
like that.
Appliances, is that just a feel good, or are those legit?
I think there are a lot of
choices?
legitimate solutions for things like that. I mean, old refrigerators have these gases in them that are not great, and they drain a lot of energy. There are ones that are now much more energy efficient. I mean, a big area of research, it sounds a little silly, but is, for example, air conditioning.
Mm-hmm.
Air conditioning is a huge part of electricity demand around the world, especially obviously in very hot places.
As the temperature goes up.
And so if you can make an air conditioner that is 20% more energy efficient, you could save so much greenhouse gas emissions and electricity at the same time from doing that. Same for heating, right? Heating is probably more of an issue in Ithaca than air conditioning. And so a lot of energy demand in this city is heating people's homes, right?
Sure.
So if you can make them more energy efficient, you can help with things like that too. So that's why I'd say, like, people looking for a silver bullet. Unfortunately, I don't think there is one. I think there's going to be 100, lead bullets. I don't know, not silver bullets, to fix everything in one
dangerous.
shot. I know that's a bad analogy, but what I mean is there's going to be 100 solutions that we're going to need to pursue. So, for example, I get asked a lot in Ithaca by people about not eating beef anymore, right? Methane emissions from cattle are actually quite high. That's about 25% or so of the anthropogenic methane emissions come from cattle. So if you eat less meats.
But then you have to also eat less cheese, because the amount of milk used for a pound of cheese is worse in terms of emissions.
Yeah, that's the part that,
it's very difficult for me personally.
Yeah, you can't just become a vegetarian and smother everything in cheese. That will not help.
Does not solve. Yeah.
So I think that all these small lifestyle adjustments, if you multiply it by 300 plus million Americans or billions of people around the world, they can start to make a dent. But the big one to never lose focus on, and where some political pressure, for example, on your people in Congress and the government, is that it's energy production and industry are the biggest releasers of anthropogenic greenhouse gases. That is very hard for an individual person to do something about, but we have to kind of keep the pressure on that we need things like carbon taxes or credits and these kind of systems that the government can do on a bigger scale than any one person can do. So that's just part of staying involved and vote, use your vote to help push these solutions as well.
Well, Phillip, thank you for sharing your work.
Yes.
And giving us hope about what's possible when scientists push the limits of chemistry and imagination. I'm Laura Riley, and this has been Research Matters. If you want to learn more about Professor Milner's research, you can check the Cornell Chemistry and Chemical Biology website. Until next time, be curious, stay hopeful, and keep watching the world with fresh eyes.